This video is going to discuss the 8.1 in Zoomdahl's 8th edition of chemistry. It starts off with talking about types of bonds. Well, we're going to talk about all the bonds here, even though the book only talks about a couple. There are ionic bonds, which are strong electrostatic attractions due to oppositely charged ions. Here's some examples: sodium chloride, ammonium nitrate, iron 3 sulfate, etc. If you look at a model of it, the anions of the chloride are bigger than the cations of the sodium ions, but there's definitely a very organized matrix here. A crystal lattice is an organized and repeating structure, and ionic compounds will have this organized structure, and therefore they are crystal lattices. While ionic bonds are very strong, you can tell because they'll have high boiling points, high melting points. They have no vapor pressure. If you spill salt on the counter, it won't evaporate or disappear. In fact, if you put salt in a pan and heat it up so the pan is smoking, the salt will not go anywhere because of the strength of the bonds themselves. Speaking of the pan, metals use metallic bonds are held together. For the most part, metallic bonds are very strong. All metals except for mercury are solids at room temperature, and that is a direct relationship to the strength of the bonds. So, kind of wordy here. They are strong, non-directional, delocalized covalent bonds. The non-directional aspect means they are going to be malleable. The delocalized means the electrons are not stuck in one place and they're able to move. This gives the ability to conduct heat and to conduct electricity, because those electrons can make a current, a stream, if you would. The attraction is between the positively charged atoms, in which the free electrons, these are going to be electrons in the valence only, not the core, are shared. So that's why it's a covalent bond. It's because the electrons, the valence electrons are being shared, and so the attraction is between multiple free atoms. The atoms themselves are positively charged cations, which include the core electrons. Here's a simple diagram of silver. As you know, silver is a +1, so each silver would have one delocalized electron per one cation. But of course, silver +1 cation will have a bunch of electrons within it. So it's not just the positive nucleus, it's the positive atom or the positive cation. The next one will be covalent bonds. Now, within covalent bonds, there's some that are stronger and weaker. Same with metallic and same with ionic. So it's hard to judge metallic, covalent, and ionic between each other unless you saw a specific bond. So all three are considered to be strong. Covalent bonds happen within molecules, not between, and what holds together what they call giant or network covalent molecules. These would be things like diamonds, graphite, glass, things like that. So it is a strong force of attraction, as all these are. That's kind of defining a bond, due to an electrostatic attraction, so it's oppositely charged type stuff. This electrostatic attraction between a shared pair of electrons and the positive nuclei for the same electrons. In other words, you have a pair, typically one electron comes from one atom, another one comes from the other, and they're attracted to the positive nuclei. That is what the attraction is. We often do a simple definition of an attraction of the atom has for a shared pair of electrons, but we really want to define that the electrons, the shared pair electrons, are attracted to the positive nuclei of both atoms. The next thing we're going to talk about is not an actual bond, but merely a weak force of attraction. They're very important in everyday life, but they are not as strong as the previous three, the covalent bonds, the metallic bonds, and the ionic bonds. So you want to recognize that they're not considered bonds and are categorized a little differently. They're weak forces of attraction that occur between molecules and single non-metal atoms, such as helium or argon, things like that. We'll talk about the 3 types in a little while. I just took that line out that was typed in there. I'm not sure what that was for, but we'll go into a whole lot more detail in this later, but not in this section. So this is kind of a quick overview. They didn't include metallic bonds here, but they did include ionic bonds, which really doesn't make a lot of sense. So there you go. These are the 3 major bonds, and the 4th is a force of attraction. We'll talk about how these 4 make solids at a later date. When working with ionic compounds, we will determine the strength of the bond using something called Coulomb's law. Now you have to understand that this happens when you have the typical metal and nonmetal, or possibly the ammonium ion and a nonmetal, or a polyatomic ion that's negative. You have to be on the lookout for ionic compounds. In which case, this is going to be your equation. 2.31 times 10 to minus 19 joules nanometers is strictly a math constant. We typically don't do the calculation, but we do more conceptual with the Q times Q over R. So we're looking for the value of energy, or usually the relative value of energy compared to another ionic compound, in which case we will compare the Q's, which are the charges, and the R, which is the radius. You won't know the radius, but you'll know which one is bigger versus smaller, so you know which one has a bigger radius or a smaller radius. So if we had sodium chloride, it's a +1 and a -1, which means Q1 is +1, Q2 is -1. Whereas if we had magnesium chloride, magnesium's a +2 and chloride's a -1. So that would multiply out to be twice as strong as sodium chloride. Now the radius in magnesium ions is actually smaller than the sodium ion. So if the bottom number is smaller, then the energy or the product of that would be bigger. So those are things we just do relative amount. You have to recognize they're comparing ionic compounds and not something else. And then you have to jump on Coulomb's law. There's something called lattice energy, which is it's a little bit different than the answer to Coulomb's law, but it kind of is relatively the same thing. So lattice energy of an ionic solid, which is what we typically talk about, especially in IB, is a measure of the energy released when gaseous ions are combined to make 1 mole of the compound. Saying that they're gaseous and ions is important, and the fact you're making 1 mole and not 2 or 3 or less than 1 is also important, because this is an energy value, and energy values are based on the amount you have. We standardize it by saying 1 mole. At the bottom, it states that lattice energy is relevant to many practical properties, including solubility, because if the lattice energy is too big, it won't dissolve in water. Hardness, the bigger the lattice energy, the harder the compound is. And volatility, the reason why ionic compounds don't just evaporate is because of these very strong forces of attraction that's measured with lattice energy or using Coulomb's law. Again, not exactly the same equation, so the values are different, but they're relating to the same thing. If you look up the definition of lattice energy, one you look up will be negative or exothermic, and one will be positive or endothermic. So the way this is defined here and in your book, it's going to be exothermic, and that's going to be the example of magnesium chloride in the first one. Well, if you flip it around, thermodynamics says you're reacting the exact same amount, except you're reacting it backwards, which means the value for delta H will be the same. However, the sign is changed. This is the way that IB defines it. It is the energy required to move the the ions away from a solid ionic compound into their gaseous separate ions, and 1 mole of the compound as part of the definition.